Okay guys, if you placed a stake 3.7 million miles from the sun, it would instantly char to a crisp. Yet NASA's Parker probe is flying right there, immersed in an inferno where temperatures exceed 1,000,000 degrees. And not only does it survive, it works perfectly, takes photos, measures magnetic fields, and transmits data. How the hell is this possible? We'll explain. Just a moment guys. Only 13% of subscribers know when we publish new videos. Make sure you subscribe and turn on the notification bell, because without it, you'll miss formats and documentaries you won't find anywhere else. On December 24th, 2024, while the world was preparing to celebrate Christmas, something extraordinary was happening 3.8 million miles from the sun's surface. A human-made object, NASA's Parker Solar Probe, was crossing through the solar corona at the incredible record speed of 430,000 miles per hour, making it the fastest human-made object ever built, a speed that would cover the distance between Philadelphia and Washington in 1 second. But that's not even the most impressive part of this journey. Parker Solar Probe achieved what seemed like science fiction just a few years ago. It literally plunged into the sun's atmosphere, into the inferno of the solar corona, where temperatures reach millions of degrees, and it survived. In fact, it continued to function perfectly, transmitting precious scientific data back to Earth. On December 27th, when the confirmation signal reached the Johns Hopkins Applied Physics Laboratory, scientists could breathe a sigh of relief. The most audacious mission ever attempted towards a star had succeeded. At this point, though, the question that all non-experts must be asking is, how is it possible that something as fragile as a probe, made of metal, yes, but also delicate integrated circuits, can get so close to the sun without instantly vaporizing? The answer to this question requires knowledge of extreme physics, visionary engineering, and a deep understanding of how heat transfer actually works in space. Let's take a step back. The idea of sending a probe toward the sun was born practically alongside the space age. As early as 1958, astrophysicist Eugene Parker published his revolutionary theory about the solar wind, that continuous flow of charged particles the sun emits into space. The scientific community was skeptical, but Parker was right, and immediately the desire was born. To truly understand how our star works, we needed to get close, very close. But there was a dual problem. First, the technology to do it didn't exist. The heat shields of that era wouldn't have withstood even a fraction of the solar heat. Initial projects from the 70s and 80s envisioned complex trajectories with gravitational assist from Jupiter, nuclear generators for power, missions that would require almost a decade just to reach the sun. The costs were astronomical, in the billions of dollars. The program was proposed multiple times and canceled multiple times. Second problem, orbital physics. To approach the sun, you can't just point in its direction. Earth orbits at 66,500 miles per hour, and any probe launched from Earth inherits this velocity. To fall toward the sun, you need to slow down, lose orbital energy. And slowing down in space requires enormous amounts of fuel that no rocket could carry. It took decades to solve both problems. In the 2000s, finally, materials technology made sufficient progress. New carbon composites, ultralight but incredibly resistant foams. And engineers found an elegant solution to the orbital problem: use Venus as a natural gravitational brake. In 2017, the moment arrived. NASA announced that the mission would be renamed Parker Solar Probe in honor of Eugene Parker, then 90 years old. It was the first time in history that a NASA spacecraft was named after a scientist still alive. Parker attended the launch on August 12, 2018, moved. He died on March 15, 2022 at 94 years old, but had time to see the first extraordinary results of the mission bearing his name. The solution to the orbital problem was brilliant in its simplicity. Instead of burning tons of fuel to slow down, exploit Venus's gravity. Parker had executed 7 close passes of the planet between 2018 and 2024, each time using its gravity to subtract energy and curve the orbit ever closer to the sun. The last Venusian flyby on November 6, 2024 placed Parker in its final orbit, an ellipse that brings it every 3 months to just 3.8 million miles from the solar surface. How close is that? If we scale down the solar system to the size of a soccer field, with the Sun at one goal and Earth at the other, Parker would be just 13 feet from the solar goal. Mercury, the closest planet to the Sun, orbits on average at 36 million miles. Parker ventures 10 times closer. The previous record holder, the German-American Helios 2 probe, stopped at 27 million miles back in 1976. Parker pulverized that record. And here we come to the crucial question: how does Parker's solar probe avoid melting? The answer lies in an engineering masterpiece called TPS, Thermal Protection System, the heat shield that protects the probe. Imagine a disk 8 feet in diameter, as big as a house door, but just over 4.5 inches thick. This disk weighs only 160 pounds, about as much as a slender person. It's a sandwich structure, two thin outer panels of carbon-carbon composite, a material also used in Formula One brakes for its ability to withstand extreme temperatures, enclose a core of carbon foam, a material so special it's normally used in medicine to replace bone portions. Hey Curious Squad, before moving on, be sure to subscribe to our channel, clicking on the notification bell, and leave us a thumbs up so you don't miss out on our daily videos. The face of the shield pointed toward the Sun is coated with a white ceramic paint, designed to reflect as much energy as possible. During close passes, this surface reaches temperatures of about 2,550 degrees Fahrenheit. To give you an idea, steel melts at about 2,730 degrees Fahrenheit. Parker's shield is literally at the survival limit of any solid material. But here comes the surprising part. Just 4.5 inches back, behind the shield, the temperature drops to about 86 degrees Fahrenheit. It's like having an oven at 1400 degrees Celsius on one side and a pleasant spring day on the other, separated by a thickness less than a brick. In this protected zone are all the probe's scientific instruments, the onboard computers, the lithium-ion batteries. Everything functions at room temperature, while just a few centimeters away rages a heat that would vaporize anything in seconds. How is such a drastic difference possible? The secret lies in a combination of factors that exploit the laws of physics brilliantly. Here's one of the most counterintuitive facts about the Sun's atmosphere. The solar corona has a temperature exceeding 1.8 million degrees Fahrenheit, but in reality it doesn't burn as you'd expect. It seems like a paradox, but the explanation is fundamental physics. Temperature measures the average kinetic energy of particles. In the corona, electrons and protons move at insane speeds, colliding at enormous energies. But the particle density in the corona is extremely low, about 1 billion times lower than Earth's atmosphere at sea level. There are so few particles that even though each one is incredibly hot, the overall energy transfer is limited. Think of this analogy. If you open your oven door while it's at 480 degrees Fahrenheit, you can't put your hand inside for a few seconds without severe burns, because hot air transfers heat slowly. But if you touch the metal tray for even a fraction of a second, you get burned immediately, because dense metal transfers energy much more effectively. The solar corona is like the oven's air, hot but rarefied. Parker's solar probe exploits this principle. The probe travels through an environment with a theoretical temperature of millions of degrees, but receives energy primarily as electromagnetic radiation, not through direct collision with particles. Just to be clear, an astronaut in a spacesuit could theoretically stand in the vacuum immersed in the corona, but only as long as something protects them from the solar rays arriving directly. Yes, because the highest heat source at that distance from the Sun isn't the corona with its merely nominal temperature of 1 million degrees, but solar irradiance. Here on Earth, 93 million miles from the Sun, every square meter of surface exposed to the Sun receives about 1,361 watts of solar energy. This is the so-called solar constant, the energy that powers Earth's climate, grows plants, and warms the oceans. Parker's solar probe, at just 3.8 million miles from the Sun's surface, receives a radiance almost 500 times greater, about 680,000 watts per square meter. Think about what that means concretely. 1 square meter on Earth receives the equivalent of a hairdryer always on. 1 square meter of Parker's solar probe's surface receives instead the equivalent of 500 hairdryers. The probe's heat shield, with its 48 square feet of surface facing the sun, is thus bombarded by over 3 megawatts of radiant power. To give you an idea, that's the energy needed to power about 3,000 homes. And all this energy must be managed by those 160 pounds of carbon and foam. Given all this, how does the shield avoid vaporizing? It uses a lethal combination of physics. The white ceramic paint on the surface reflects about 80% of incident radiation, bouncing it back into space. The remaining 20% is absorbed, heating the shield up to 2,550 degrees Fahrenheit. At that temperature, though, the shield itself becomes a powerful emitter of thermal radiation, radiating energy into space in all directions through the Stefan-Boltzmann law, and thus reaches a thermodynamic equilibrium. As much energy enters as exits, keeping the temperature constant. The internal carbon foam, with its extremely low thermal conductivity, prevents this heat from propagating to the backside. The result? An extreme temperature gradient, 1400 degrees on one side, 30 degrees on the other, in just 4.5 inches of thickness. This equilibrium is extremely delicate. If the shield misaligned even a few degrees relative to the sun, radiation would directly strike the unprotected instruments, vaporizing them in a matter of seconds. This is why the probe is equipped with autonomous attitude control systems. Sensors continuously monitor the shield's position, and small thrusters instantly correct any deviation. In 8 minutes, the time a signal takes to travel between the sun and Earth, the probe would already be destroyed. It must manage everything on its own. But why face all this? What are we learning that is so important to justify a $1.5 billion mission? Well, the sun isn't just a ball of gas that warms us. It's a violent nuclear dynamo traversed by magnetic fields that generate eruptions, launching billions of tons of plasma into space at insane speeds. These solar storms can cause enormous damage. In 1989, a geomagnetic storm left 6 million people in the dark in Quebec for 9 hours. In 1859, the Carrington storm was so powerful that telegraph operators received electric shocks. Today, our civilization depends on technology incomparably more. Satellites, GPS, bank transfers, air traffic control, all vulnerable to solar storms. A superstorm today could cause trillions of dollars in damage. To predict and protect ourselves, we must understand how these events are born. And here lies one of the great mysteries. The sun's surface has a temperature of about 9,930 degrees Fahrenheit. But rising into the atmosphere instead of cooling down, the temperature skyrockets to over 1 million degrees in the corona. What heats the corona to such extreme temperatures? The energy must come from the sun, but how is it transported and released? Scientists have proposed various theories. Perhaps they're magnetic waves propagating from the surface and dissipating their energy in the corona, like sound waves that become heat when they break. Perhaps there are thousands of small magnetic explosions, called nanoflares, too weak to be observed individually but collectively pouring out immense energy. Or perhaps it's magnetic reconnection, when the sun's magnetic field lines break and reconnect, releasing energy like a stretched rubber band that snaps. But before Parker Solar Probe's arrival, it was impossible to verify these theories. No instrument had ever physically entered the corona to measure it up close. And now the probe is proving the first direct answers. Its FIELDS instrument measures electric and magnetic fields with unprecedented precision. SWEEP analyzes solar wind particles. The WHISPER camera captures extraordinary images from inside the corona. The most recent images show never-before-seen details. You can see the turbulent plasma eruptions crossing the field of view at 1 million miles per hour. High-energy particles hitting the sensors, creating a snowball effect. Parker is filming space weather from inside the storm. Parker will continue its mission at least until 2026, with close passes every 3 months. Each pass brings new data, new puzzle pieces to better understand our star. It will remain in the final orbit as long as it has fuel to maintain its orientation. This is crucial. It must remain perfectly aligned with the shield facing the sun. If it lost this orientation, it would be destroyed in seconds by direct exposure. When it runs out of fuel, probably in a few years, it will continue to orbit silently, a technological monument to human curiosity. There's no plan to recover it. It will remain there in its perpetual journey. But Parker's legacy goes far beyond scientific data. It has demonstrated that we can design technologies to survive in the solar system's most extreme environments. It has paved the way for future, even more audacious missions. And it has reminded us that the boundary between impossible and possible is thin. It's often just 4.5 inches, the thickness of a heat shield that separates human curiosity from stellar hell. Eugene Parker attended the launch in 2018 at 91 years old. He died on March 15, 2022, but saw the first extraordinary results. His dream of touching the sun came true, and every time Parker's solar probe crosses the solar corona at nearly 430,000 miles per hour, protected by that extraordinary carbon shield, we're writing a new chapter in the history of humanity's exploration of the universe. Okay guys, what do you think? Did watching this video raise any doubts or questions? If so, it would be strange if it didn't. Please feel free to let us know in the comments. And if you want to learn more, check out our viral video here. Why is it harder to crash into the sun than to leave the solar system?